Hey everyone, today we're going to talk about section 8.5, deals with the last of our series test, the alternating series test, and the concepts of absolute and conditional convergence. Okay, so let's start out with a definition. An alternating series is a series whose term sine alternates between positive and negative. And is of the form sigma, say n goes from 1 to infinity, not necessarily, -1 to the n plus 1 en. Okay. So you can see here that we have this -1 raised to a power. We've seen a few of some series that look like this, but we'll talk more in depth about the convergence here. So you can see when n is 1, if n is equal to 1, we get -1 squared times b1. So because -1 squared is +1, we just get b1. Now when n is 2, 2 plus 1 is 3, -1 to the third power is -1, so we get -b2. And when n is 3, we get fourth power here, which makes that positive. So plus b3 and so forth. Minus b4 plus b5 minus so on and so forth. Okay. So let's start with an example. Write the summation notation. Following. Say A is 1 minus a half plus a third minus a fourth and so forth. So if we take a look at these terms, we want to make try to write this as sigma notation. We notice that there is an alternation of the signs here, so we're going to have to put in -1 to some power. Now if we start n at 1, we want the first term to be positive, so we have to have an even power up here for the first term, an odd power for the second, and so on. So that would be n plus 1. When n is 1, we get a 2 here, so that would be positive. And then the terms in the series, if we just look at the positive terms, it's just like 1 over 1, 1 over 2, 1 over 3. So our terms follow this guy here. Or sometimes we might see it like this. Same thing. Okay? B, let's do -1/2 plus 2/3 minus 3/4 plus 4/5, and so on. Okay. So if we take a look here, we see that we have some sign alternation. The first one is negative. So if we start n at 1, we want -1 raised to an odd power first, and then an even power, so we can get away with just having n there this time. When n is 1, we get -1. When n is 2, we get +1. So we get this correct alternation in the signs. And then let's take a look at the terms of the series here. We have 1, 2, 3, 4, so that's just going to be n over 2, 3, 4, 5, so that's just n plus 1. So we have this series here. All right, so our goal here is to figure out when do these type of series converge. So let's look at the alternating series test. So here's the test itself. Alternating series. Sigma n goes from 1 to infinity, -1 to the n plus 1 bn. Converges if two things are true. First, limit as n goes to infinity of the terms of the sequence, right? We're looking at just the positive terms, goes to 0. And the terms are monotonic decreasing. Okay. So again, each subsequent term is smaller than the preceding term. Okay? So let's think about why this works. Well, we can kind of go in a graphical approach here. Suppose we know that a series, any general series will converge if the limit of its partial sums goes to a finite value. This is finite there, right? So let's say we have this number line here. And what I'm going to do is just measure the partial sums along this axis. So let's say we have a 0 here, right? So if you recall from up here, let's say our first term's positive, and then our second term's going to be negative. So let's say we have some arbitrary b1 value. So, of course, when we start out, we have nothing to add to, so we have 0 there. So the first partial sum is just the first value in the series. So let's say we add b1 okay, so we have started at 0. Then when we add that first term, so the first term sends us to some positive value. b1 is positive, of course. So here is the first partial sum. Okay, S1 would be somewhere on this axis. Now, the second term in the series is negative, right? So we're going to take some away from this first partial sum to get the second partial sum. Now, in order for us to see convergence, if we follow both of these properties, the next term in the series is going to be some smaller value than the previous term. So b2's magnitude is going to be smaller than b1. So when we subtract b2, it's going to put us backwards a little bit, right? Because b2 is negative. So it's going to put us back some, let's say, to here. And we know that the magnitude of b2 is smaller than b1, so we're not going to go too far here. So our second partial sum would be right here. Okay. Now b3 is, let's say, a positive number, but b3 is smaller than b2, so that or equal to. So that's going to put us maybe right here. All right. So we're the second partial sum, we're going to add some positive term. It's going to increase the third partial sum to here. Okay. And then we continue to do this ad infinitum. This is an infinite series. So our fourth partial sum would be here because b4 is a negative value, so it's going to send us in the opposite direction, but it's a smaller magnitude than b3. And we do that forever and ever and ever. So you can see that the, let's see, here would be S5, here would be S6. So you can see we're honing in on some particular value, that would be the value of the infinite sum, right? Infinite partial sum here. So you can see it's converging to some finite value. If this is not true, or this is not true, of course, then let's see what happens. Do the same kind of analysis. Say here's 0. So we would first add B1, right? Giving us our first partial sum here, S1. Now if B2, so remember that the condition on the next term would have to be less than in order for it to converge, like we saw here. If it's not true, if the second term is larger, then that's going to put us past 0, right? It's larger, we're subtracting more than we added in the previous term. So that's going to put our second partial sum right here. And then if we continue that process, if the next term is larger, it's a bigger positive term than the last one, that's going to put us maybe out here. So our third partial sum is there. So if we continue that process forever and ever, it's going to send us, the partial sums are going to diverge. You can see that they are going away from each other each time that we do this. So this would be S4 and S5, and S6 would be even farther over here. S7 would be farther in the right-hand direction. So we have to have that condition on the terms of the sequence. Okay? So let's do an example. Which of the series from the previous example converge? Okay. So let's look back. All right, so we have this guy here. A was sigma n goes from 1 to infinity, -1 to the n plus 1 over n. FYI, this is called the alternating harmonic series. Right, we know that the harmonic series is sigma 1 over n. Here we have the alternation, so we call it alternating harmonic series. So whenever we see this, and the best option to use when we're trying to test the convergence of something that has an alternating sign is using the alternating series test. So this is a dead giveaway that you should be using the alternating series test because it has that alternating term there. So let's take a look back at the conditions. We need two things to be true. We need the limit as n goes to infinity of bn to be equal to 0. And we need the terms in the sequence to be decreasing. Okay. So let's take a look here. First condition, we need to test to see if the limit as n goes to infinity of bn is 0, right? So what's bn here? Well, bn, if we look back at the definition, bn is just all the positive terms. So we don't consider the sign change here. We just consider the positive terms in the series. So in this case, that would be looking at this limit as n goes to infinity of 1 over n. And we know when we throw an infinity here, it's 1 divided by a very big number, and that number just keeps getting bigger and bigger. So this value goes to 0. So the first condition is true. The second condition, we need to show that the subsequent terms are decreasing for n greater than some n value, right? So it doesn't necessarily have to be monotonic decreasing, but at some point, all the terms in the series, all the subsequent terms have to be less than the previous terms after some value of n here, okay? So to show this, what we can do is either do this algebraically, or we can use the derivative, right? So we know that 1 over n, if we can treat this as a function, we can take its derivative, and if the derivative is a negative value for all n greater than some arbitrary n, then we know that this sequence is decreasing here, okay? So I'm going to do it two ways. I'm going to do an algebraic approach for this and the calculus approach for this. So algebraic approach. What we want to show is bn plus 1 is less than or equal to bn for some values of n. Okay, so note we want to show that bn plus 1 is less than or equal to bn. So what we're going to do is just sub n plus 1 into our bn and show that this relationship is true at some point, right, for some n value greater than some arbitrary n. So all we need to do, so bn plus 1 less than or equal to bn means 1 over n plus 1 less than or equal to 1 over n. So what we need to do is just manipulate this so that we are absolutely sure that the inequality is true. So we'll cross multiply here. N is less than or equal to n plus 1. Now we ask ourselves, is this true? Well, yes, right? Like if we could subtract n from both sides and get zeros less than or equal to 1, this is always true, right? Therefore, since condition 1 and 2 are true, this series converges. Now, calculus approach to this, we consider f of x equal to 1 over x. So we just consider the corresponding function of x to our series. And what we want to do is show that the derivative is always negative, well, for some arbitrary n, right? So what is f prime of x? Well, this is like x to the negative 1, so differentiating, we get negative 1 over x squared. Right? And this is always less than 0, right? Always less than 0, which implies f is decreasing. So bn plus 1 is always less than or equal to bn. So since 1 and 2 are true, series converges. So it's simple as that. This is not a very tough test to do. Let's do our second one. So that series was sigma n goes from 1 to infinity of negative 1 to the n times n over n plus 1. All right, no special name for this one, so let's check our limit first. We need a limit. So n goes to infinity of bn to be 0. So what is bn? Bn is just the positive terms of the series, so that's n over n plus 1. This is equal to 1, right? same exponent, same degree on the top and bottom, so we just take the ratio of the coefficients here. So this tells us that the alternating series is not going to be very helpful for us here. So what we need to do is try the test for divergence. So if this happens, consider nth term test for divergence. Okay. So recall that the nth term test says we need to take the limit of the terms of the series and see what happens there. All right. So we take the limit as n goes to infinity, -1 to the n, and over n plus 1. Now let's think about this. So we have the alternation in the sign, and this guy goes to 1, right? So this limit does not exist, right? Why is that? Well, these guys are going to, so we can actually, using limit properties, rewrite this as the product of two limits. All right. So why is this? Well, you can see here this guy goes to 1, so we're just dealing with the limit as n goes to infinity of -1 to the n. Now, for certain values of n, this is +1, and certain values of n, this is -1. So the limit does not go to the same value from the left and the right-hand sides. It does not approach a particular value. That's why it does not exist. Okay? So based on this, you can tell whether the divergence happens or not, right? So if this happens, this is not 0, then this nth term test is going to be non-existent, okay? So this series diverges. All right, let's do another. Determine if the series converges. Let's do sigma n goes from 1 to infinity, -1 to the n, times 3n over 4n minus 1. So you may want to try this one on your own before I do the solution. So you can pause here and do that, but I'll be going through the solution now. So the first thing you want to do is always check that limit. Limit n goes to infinity, bn, which is the limit for the positive terms of the series here. This is 3/4, right? Same degree, so just take the ratio of the lead coefficients. This is non-zero, and as we saw in the previous example, this implies divergence, right? B. Let's try -1 to the n plus 1, n squared over n cubed plus 1. All right, so let's check our first condition, check our limit as n goes to infinity of positive terms to a larger degree at the bottom here, so this limit goes to 0. So that condition is met. Now for our second condition, we can do an algebraic approach or a calculus approach. I like the calculus approach, of course, right? So let's take a look. So consider f of x equal to x squared over x cubed plus 1. So f prime of x would be, well, we have to do a quotient rule here, so derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom square. So let's see what we get. We'll have 2x to the fourth minus 3x to the fourth, so that's just negative x to the fourth. And then 2x plus 2x over the bottom square. Now, we need to show that this is negative for particular values of x. So is this true? Is this less than, when is this less than 0? We ask ourselves. Well, we can solve this, so rewrite that. Less than 0, that is. Strictly less than. So solving, we can just multiply by x cubed plus 1 squared on both sides. That'll leave us with x to the fourth plus 2x is less than 0. We can factor out a negative x here, leaving us with x cubed minus x less than 0. Excuse me, x squared, x cubed minus 2 is less than 0. Okay. So how do we determine for what values of x this is true? Well, we can do a sign test actually. So for what values of x is this equal to 0? Well, x would be 0 here. It's equal to 0 when x is 0, or x is the cube root of 2, right? So I'm going to do a sign test. 0, cube root of 2, let's say is there. So we'll be looking at negative x and x cubed minus 2. Okay. So what I'm going to do is pick values. Of course, we can't be equal to. I'm going to test the sign of this guy in each of these intervals. So we're going to pick a value in each of these intervals and then determine to see whether it's positive or negative. So let's pick a number here. So like negative 1. If x is negative 1, what's the sign of this guy? Well, that would be a positive. If x is negative 1 here, this would be a negative. Therefore, negative x times x cubed minus 2 is negative in this region for all values here. So that would be a solution set, right? How about in here? Well, what number is in between 0 and the cube root of 2? The cube root of 2 is slightly larger than 1, so we can choose 1 here. So this sign would be negative. And if x is 1 here, this sign is also negative. Therefore, this product would be positive here. Okay. And then lastly, pick a number in this interval. So we don't have any solutions to this inequality in this interval. So how about here? So the number that's in this region would be like 2. Pick 2. Plug in 2, we get a negative. Plug in 2, we get a positive. Negative times a positive is a negative. Okay. So we do have solutions to this inequality here. All right. So what does this tell us? This tells us that f prime of x is less than 0 for x greater than cube root of 2. All right. This implies that Bn plus 1 is less than or equal to Bn for all n greater than the next integer of 2. So this satisfies, again, because the derivative is negative on this interval, for all of the terms in the sequence follow this pattern for when n is greater than 2. It's the next integer after the cube root of 2. So this satisfies our condition on Bn plus 1 is less than or equal to Bn for some arbitrary value of n. In this case, it's specifically 2. Thus, the series converges. Let's try one more. Let's see. Sigma n goes from 1 to infinity of n, negative 1 to the n plus 1, and e to the negative n. So let's check our limit. Limit as n goes to infinity of n e to the negative n is what? Well, if we plug in, we'll get infinity times e to the negative infinity. That's infinity times 0. That's an indeterminate form. So let's use L'Hopital's rule. When we rewrite this, we'll sink that e to the n down. Put in infinity, get infinity over infinity. So let's use L'Hopital. So we're looking at the limit as n goes to infinity of 1 over e to the n. And what's this limit? Well, it's 1 over infinity. If we put in a giant number, that's a big number down at the bottom. 1 divided by a big number goes to 0. Condition 2, we need to show that the terms in the sequence are decreasing, so we consider our derivative. So f prime is, use the product rule here, so derivative of the first times the second plus derivative of the second times the first. Or e to the negative x minus e to the negative x times x. So we need to figure out for what values of x this is less than 0, right? So e to the negative x minus e to the negative x times x is less than 0. And then solve this guy. So you can utilize factoring to do that. Factor out e to the negative x. You get 1 minus x is 0. And we can do a sign test here. So note that e to the negative x is never equal to 0. Right? And in fact, it's always greater than 0, right? E to the negative x is always a positive number. So this is always positive. So all we need to do is figure out where this guy is negative. 1 minus x is less than 0 when x1 is less than x or x is greater than 1. This implies Bn plus 1 is less than or equal to Bn for n greater than 1. That's true. This is true. Therefore, the series converges. do one last one. Sigma n starts at 2 to infinity, -1 to the n plus 1 times 1 over natural log of n. Let's look at our first condition. We need this limit to be 0, is it? Well, what's the natural log doing as n goes to infinity? Natural log also goes to infinity, so that's 1 over infinity, that's 0. Condition 1 is met. Now for condition 2, let's consider our derivative. F prime would then be, we can consider this as like natural log of x to the -1, right? So chain rule, -1 times natural log of x to the -2 times the derivative of the natural log of x, which is 1 over x. Or -1 over x times the natural log of x squared. So what we want to do is to figure out when this guy is decreasing, right? So when is f decreasing is when f prime is negative, right? So let's get our critical values here. Critical values for this. We'll note that this is never equal to 0. This is never equal to 0, but there are some breakpoints in here. So note that this is undefined when x is 0 and when x is 1. So we set up a sign test. 0 and 1 are the critical values. Again, critical values occur when the derivative is equal to 0 and when it is undefined. So you can see here that when x is 0, we get undefined. When x is 1, we also get undefined because the natural log of 1 is 0 as well. So let's see. Here, we do our sign test. The natural log of x squared. Note we cannot have solutions in this interval because the natural log is can only take on positive numbers. If we look here, if we put in like something like a half, we'll get a positive over the natural log of 1/2 is negative, but when you square it, you get a positive. So the product here is positive, and then -1 divided by a positive is negative. And then you can see if we put in something like 2, we get a positive and a positive, so this gives us a negative as well. So the so f prime is less than 0 for all x greater than 0 and x. Thus, bn plus 1 is less than or equal to bn for all x, excuse me, all n greater than 1, right? This this is satisfied the series converges. Okay, so we can fill in our alternating series test column. I've actually misplaced the original one that I started, so I'll just do that here. So you can go ahead and take out your table. Okay. So we had our form converges if, diverges if, comments. So the form for our series was n goes from 1 to infinity, -1 to the n plus 1 bn. Converges if both of the following are true. The limit as n goes to infinity of bn is 0. And bn plus 1 is always less than or equal to bn. Diverges if this limit is not 0. All right, we saw that. And technically, this is by the nth term test. Okay. And we can make a comment. Use f of x, or f prime of x, to determine condition 2. Okay. All right, so that completes our series tests. The second half of this section deals with absolute and conditional convergence. Okay. So there are two types of convergence. One, absolute convergence, and two, conditional convergence. So, definition. A series is said to converge absolutely if the absolute value of the series converges. So if we look at the absolute value of all the terms and sum those, if that converges, then we say that the series converges absolutely. Corollary to this is if the series converges absolutely, then the series converges. Okay. So if we find that this the series of the absolute values of the terms converges, then we know that the original series converges too. Definition. Series is said to converge conditionally if the original series converges and the absolute value series diverges. So basically what the difference is between these is that absolute convergence is basically like a stronger type of convergence than conditional convergence. So we're just defining them in this way. Okay? So let's do an example. Show that sigma n goes from 1 to infinity, -1 to the n plus 1 over n squared converges absolutely. Okay. All right, so how do we do this? Well, we know that by definition, we know a series converges absolutely if the sum of all the positive terms of the series, the absolute value of the terms of the series, converges. So that's the first thing that we want to do. We want to look at this. So we consider this series here. Okay. So we're just going to take the absolute value of all of these terms. Well, what happens? When we take the absolute value, the alternation goes away. So everything becomes positive, right? So this is equivalent to this series here, 1 over n squared, right? That, again, the -1 just becomes positive with the absolute value. So if we take a look at this series, does this series converge? If this series converges, then this guy converges absolutely. Okay? So does this series converge? Well, how do we know? Well, this is a special type of series, right? This is called a p-series, right? So the p-series we know converges if this power is greater than 1. And it is. This converges by p-series test. Thus, this guy converges absolutely. All right, let's show that sigma n goes from 1 to infinity of -1 to the n over n to the 1/2 converges conditionally. Okay. So recall, with conditional convergence, we know that this guy is not going to converge absolutely, but the alternating series may converge, right? So again, we know a series converges conditionally if the original series converges, but the absolute value series diverges, okay? So let's see. So check always for absolute convergence, checking for absolute convergence. We consider the absolute value of this series. Again, that just knocks out all the negatives. So we're looking at n to the 1/2. 1 over n to the 1/2. Does this series converge or diverge? Well, it diverges, right? This is another p-series, but p is not greater than 1. Diverges by p-series test. So this implies sigma n goes from 1 to infinity, negative 1 to the n over n to the 1/2 does not converge absolutely. Okay. Again, it doesn't converge absolutely because the absolute value series does not converge. Now we need to check to see whether this guy converges or not. Okay, so we've checked for absolute convergence. Now, checking for general convergence. Let's say conditional. So we need to employ a series test that's going to handle this guy right here. So what's the best series test for something that looks like this? Well, it has alternation, right? So checking for conditional convergence, use alternating series test to do that, right? So we need to check two things. We need to check the limit as n goes to infinity of Bn is 0. In this case, Bn is just the positive terms here, so 1 over n squared to the 1/2. As n goes to infinity, the denominator does 2, so this is 0. Check. For condition 2, consider f of x equals 1 over x to the 1/2 to the 1/2. So f prime would be, this is like x to the negative 1/2, so negative 1/2 x to the negative 3/2, or negative 1 over 2 x to the 3/2. Our critical value is 0 because that's where this guy's undefined. So in this range, our derivative is, well, in this case, we can't have solutions, right? Can't have solutions because we're taking the square root here, so there are no values here that are negative. It's not in the domain of our original function. And then here we will see for when x is a positive number, we'll get a negative value here. So f prime is less than 0 for all x greater than 0. So Bn plus 1 is less than or equal to Bn for all n greater than 0. Thus, the series converges and converges conditionally. So we've just checked to see if the original series that we had to begin with was convergent. It is. Its absolute value series is divergent. Thus, it follows the definition of conditional convergence. Let's determine if the series converges absolutely, conditionally, converges conditionally, or diverges. So we have this series here, sigma n goes from 1 to infinity, negative 1 to the n, times 2 to the n over n squared. So whenever you're faced with this problem of finding absolute convergence or conditional convergence, always test for absolute convergence first. Why do we do that? Well, note that that is because of this corollary, right? If we have absolute convergence, then we automatically know that the series converges as well. So always test for this first, and if this doesn't work, then we're going to test for conditional convergence or divergence, okay? So checking absolute convergence here. We want to consider this guy absolute. That just kills the negatives, right? It's 2 to the n over n squared. Right? So let's see. We need to determine whether this series converges or diverges. So what can we do here? What series test would work best for something that looks like this? Well, we can always check the nth term test, right? The nth term test tells us for divergence. We could use that. We also have some term that has like a power of n, so ratio test would be a good one to use here as well. Either of these would be fine. I'm going to use the nth term test first to see this guy diverges. The nth term test says take the limit as n goes to infinity of this guy. And if it is non-zero, then we have divergence, right? So let's see what we can do. As n goes to infinity, this guy goes to infinity, this guy goes to infinity, so we can use L'Hopital. Limit as n goes to infinity. The derivative of 2 to the n is 2 to the n times natural log of 2. Over, the derivative of the bottom is 2n. If we test this limit, this guy goes to infinity, this goes to infinity. We can use L'Hopital again. So the limit as n goes to infinity of derivative of 2 to the n, again, is 2 to the n times natural log of 2 times natural log of 2 over 2. Testing the limit again, this goes to infinity over 2, that's infinity, right? So what can we conclude? So we just tested for absolute convergence here. We've got divergence of the absolute value series. Thus, the series doesn't converge absolutely. Okay. Now let's test for conditional convergence. All right, so for conditional convergence, we test to see if the original series, this guy here, converges or diverges. Of course, the best test to use, because we have this alternating term, is the alternating series test. 9 times out of 10, that's what you'll be using when you can test for conditional convergence. Okay, so the alternating series test, AST, let's abbreviate. We need to check our first condition, that this limit of 2 to the n over n squared goes to 0. We just saw from the previous limit that this is infinite. So we're done, right? So we know that it does not converge absolutely. It does not converge conditionally because this fails the alternating series test or the nth term test here. Thus, the series diverges. Again, that is non-zero. Okay. Let's try another. Same idea. So how about sigma n goes from 0 to infinity. Right, how about negative 1/4 to the n? Okay. All right, so note that we have this alternating series, right? This is because we can treat this as negative 1 to the n times 1/4 to the n. That's the same thing, right? So we can just decompose this into its alternating term here and the positive terms of the series. So testing for absolute convergence. We want to consider the absolute value of this guy. Or n. So taking a look at this series, does this converge or diverge? Well, note that this is a special type of series, right? This is a geometric series. It's just a ratio being raised to a power. And we know that this will converge by geometric series test. So it's a good idea to get practice with identifying this special type. In particular, there are really only two that are very simple, the p-series and the geometric series. So we know that this guy converges, therefore we can conclude what? That we have absolute convergence. Thus, sigma negative 1/4 to the n converges absolutely. Okay. And we're done. We don't need to check for conditional convergence because we already know it converges absolutely. That's the strong type of convergence here. Last one. Let's go sigma n goes from 1 to infinity of cosine of pi n over n squared. Oh, excuse me, just cosine of n over n squared. Okay. So if you take a look at this one, actually, we know, actually, yes, let's put the pi back in there. Pi n. Pi n. Okay. So let's take a look at this. So we have this weird trig term in there now. So what's happening with that? That's a little bit weird. So just note that if we have the cosine of pi n, if n is 1, then we get the cosine of pi. The cosine of pi is negative 1, right? So let's write out some terms of the series first before we do anything with the convergence. The first term would be the negative 1 over 1 squared. The second term is when n is 2. This would be 2 pi. Cosine at 2 pi is 1, so this would be 1 over 2 squared. Third term would be the cosine at 3 pi, which is negative 1 again, over 3 squared. And then the fourth term would be positive, because cosine of 4 pi is positive, and so on and so forth. So you can see we have this alternation because of the nature of the cosine function. So this is equivalent, you can actually rewrite it without that term as negative 1 to the n times 1 over n squared. So we can just work with this guy now because these are equivalent to each other, right? So testing absolute convergence. We want to consider the absolute value. We'll be using this form, which is just the 1 over n squared. And we've seen this several times today. This is a p-series. P is bigger than 1, so it converges by p-series test. Thus, sigma n goes from 1 to infinity, cos pi n over n squared converges absolutely. All right, so you should be able to start your homework assignment now.